Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video where we are going to see uniform plane microwaves and its reflection. Here we are in first unit of the microwave engineering. The unit is Introduction to Microwaves. So I hope it is very clear that microwaves is nothing but the electromagnetic wave with a specified frequency range of 1 GHz to 300 GHz. Various microwave engineering applications I have now introduced to you people, along with the knowledge of various microwave devices. Either they may be onto the vacuum tube platform or semiconductor platform. The microwave system practical test bench is also introduced, along with the knowledge of having the principle of operation for the velocity modulation. We have gone through electron motion in electric, magnetic, and finally electromagnetic field. So for having the operation of microwave devices, it is very important to have the knowledge of uniform plane microwave and its reflection. So let us begin with the topic. So as we talk about uniform plane microwave, very first of all, it is basically the wave. And when we talk about the plane wave, it is the wave which is having the constant phase. So generally for electromagnetic wave, we can have one diagram where the electric, magnetic and the direction of propagation, electric and magnetic being the vectors, are mutually perpendicular to each other. So let us have the diagram. So here we take the help of rectangular coordinate axis. So let us say this is the positive z axis. So to positive z axis, here it is x axis perpendicular to it at the intersection point, that is origin. And at the origin we have the third axis also perpendicular to the both x and z, that is the y axis. So here we consider that the electric wave is having the variations along the x-axis. So here we can draw such a wave for positive and negative sides of the x-axis here. Here it is the origin, and simultaneously here we have another wave. Let us say it is magnetic wave that is having the variations along the positive and negative y sides. So these vertical lines can show you the vector representation for E. So the component I can say will be E suffix x. Similarly, these arrows indicate you the vector nature for the magnetic wave here. So for magnetic wave, we represent with its magnetic field intensity, so it is H vector, and here for y we have the hy component. So z is positive z, the direction of propagation of wave. Now coming back to our title, we have the title Uniform Plane Microwaves. So uniform plane microwaves is nothing but the electromagnetic wave with the microwave frequency range having a constant phase along with the constant magnitudes. So as we are talking about the constant magnitude and the same phase for the wave components here, so we shall be having the representation of equations like del E by del X, or if you take del E by del Y in general, if you take the direction of propagation of wave to be the positive z axis. So these partial differentiations of electric field intensity magnitude will be equal to 0. So these are the partial differentiations with respect to the space components x and y here. Or for magnetic field intensity component also, if you take the magnitude in consideration, that time we may write del H by del X is equal to del H by del Y. This is also equal to 0. So these two equations indicate that there is no variation along the x and y components if you take the diagram into consideration. Now, in one of our previous video, we have been introduced to the microwave wave equation. These are basically the wave equations for any electromagnetic wave. The two equations are there, one for the electric field and another for the magnetic field. So, if we are considering the medium through which this microwave is going to propagate to be a lossless medium, so for any medium, generally we have the three components. So, the parameters actually, the first one is the conductivity, that generally we denote with the help of sigma here. The another one is permittivity of the medium, that is epsilon, and the third one is the permeability of the medium, mu. So conductivity is generally given in terms of moles per meter. Moles per meter. The permittivity of the medium into farads per meter, permeability into Henry per meter. So if you consider sigma is equal to 0, the general microwave equation here for electric field we can write. It will be del 2 Ex here divided by del Z square is equal to mu 0 epsilon 0 del 2 Ex divided by del T square. So if you recall the wave equation for electric field, onto the left hand side it used to be del square. So that del square was actually the Laplacian operator. It is basically scalar into the nature. So it has the three components x, y and z. As we consider the propagation of wave in only positive z direction, the only one partial derivation with respect to z here we consider with the second order differential, and we consider that E electric field into the x-axis. So along with this equation, the microwave equation for the magnetic field can also be written. So it will be del 2 Hy divided by del Z square is equal to, into the right hand side we have mu 0 epsilon 0 del 2 Hy by del T square. So on the right hand side we have the time differential for the Hy component, whereas onto the left hand side we have the space differential with respect to the Z component here. So this is, let us say, equation number 2. Now assuming no loss for the electric as well as the magnetic component, very first of all the Ex component can be given. So I write the equation, generalized equation for Ex. So it will be equal to E0, the initial magnitude, in multiplication to the exponential, where e to the power j in bracket omega t minus beta z it will be there. So here omega is the angular frequency, t is the time parameter, beta is the phase shift constant. So in this equation we have j in bracket omega t minus beta z, where omega is the angular frequency, t is the time parameter, beta is the phase shift constant. So phase shift constant for any wave propagation should be non-zero, otherwise the wave should not be proceed into the medium. Now if we have the Ex component, we must have the Hy component obtained by using the equations that we have studied up till now. So Hy component using the Ex can be obtained as, it will be square root of, here in the numerator we have epsilon 0 divided by mu 0 into Ex component. So I outline these two equations which are very useful to us. From these two equations, generally if we take the ratio, that is Ex divided by Hy, so it can be represented at eta suffix 0. So eta suffix 0 is the intrinsic impedance, and from the above formula we can simply write it is square root mu 0 divided by epsilon 0. So if you substitute these constant values, so this is the permittivity of the free space and this is permeability of the free space, we obtain the value approximated rounded to the 377. The unit of measurement should be ohms here. Now here in this case, this intrinsic impedance you can compare with respect to the Ohm's law also. In the Ohm's law there is a relation between the voltage and current here, where the proportionality constant is resistance, capital R generally we denote here. So capital R can also be written as the ratio of voltage to the current. So if you consider here E, so the unit here it is volts per meter, and if you take HY, it is the magnetic field intensity, the SI unit is amperes per meter. So simply V upon A will be nothing but the ohms here. So this is the intrinsic impedance for the microwave if it is propagating into the free space. Now if such microwave is having a propagation, so what is the velocity of that particular propagation? So velocity can be denoted as V suffix 0, where the value can be derived again from the two medium parameters that are permittivity and permeability. So it is the multiplication of mu 0 and epsilon 0, which is under root in the denominator here. So again, if you substitute the values, you come to know that the velocity of microwave when propagating into the free space, it will be nothing but 3 into 10 raised to power 8 meter per seconds. Now I hope that we are now familiar with the term uniform plane microwave. Now as the objective of this particular topic is to get the understanding how exactly the microwave will be behaving when it will be propagating through different kinds of medium that will be coming across when we work with different microwave devices. So designing, analyzing microwave engineering system is our motive here. So here we shall be having a knowledge of boundary conditions also, because while having propagation, microwave has to switch from one medium to another medium. So you may be having a background from the electromagnetic field theory where a boundary separates the two media here. So here consider that this line separates medium 1 from medium 2. So for medium 1, we can be writing sigma 1, mu 1 and epsilon 1, the three parameters that are characterizing the medium 1 here. Similarly for medium 2, we can write sigma 2, then mu 2, then epsilon 2. So as we consider that there will be the microwave propagating through the medium 1, it will be incident onto this particular boundary, and then it will be further carrying its journey into the medium 2. So here the microwave is having electric and magnetic components. So the components may be either tangential to the boundary or normal to the boundary. So normal means perpendicular here. So if these are parallel to the boundary surface, we say they are tangential component. We can denote E suffix T, H suffix T for tangential. Along with we can have D suffix T, then B suffix T. D and B are the flux densities corresponding to the electric and magnetic field. Similarly, if we are talking about the normal components, so normal means perpendicular here. So here they shall be En, then Hn, Dn or Bn here, that we can interconvert with the help of the Maxwell's equation or other equations. Now for the general case, we can write the boundary conditions with the help of four equations. The first equation we can write, here we have Et1 is equal to Et2. So this equation gives us the information that the tangential component of electric field intensity into the medium 1 is the same as like the tangential component of electric field intensity into medium 2 also. So here this tangential component is continuous across the boundary. Now the second equation we can go for, that is dn1 is equal to dn2 plus rho s. So if the boundary separating medium 1 from medium 2 is having certain amount of charge onto that surface. So we account it onto the rho suffix s here. So this is surface charge density. So here we don't find dn1 is equal to dn2. dn1 is equal to dn2 added with this surface charge accounted into the rho s here. So the normal component of electric flux density is discontinuous across the boundary. Next to that, we can have the third boundary condition where we write here ht1 is equal to ht2 added with j suffix s here. So here we have the tangential component of magnetic field intensity discontinuous across the boundary. For ht1, ht2 should be added with j suffix s. So j suffix s is the cross-sectional conduction current density. So for having the first two equations, generally we have for the tangential components, we have such a loop here, and for this particular loop we take the help of the Stokes theorem and we generally derive the tangential boundary conditions here. Whereas for the normal components we take the help of such a pillbox shape here and we derive the boundary condition for the normal components here. The fourth boundary condition in general can be given as bn1 is equal to bn2. So here we say that the normal component of the magnetic flux density is continuous across the boundary. So with these four boundary conditions, we can have the changes accordingly if we put the variation of sigma, the conductivity, the variation of permittivity, epsilon, or the permeability mu here. So the boundary conditions for any medium change, we can have formulation with respect to the behaviors of the electric and magnetic components. Now we come to the title of our topic. The title of topic was Uniform Plane Microwaves and Reflection. So I hope you are now very well familiar with uniform plane microwaves. Now if this uniform plane microwaves is encountering any boundary surface where onto the another side there is a perfect conductor. So generally the perfect conductors are never penetrated by the electromagnetic wave. There will be a complete reflection. So the reflection may be of two types, either normal incidence or the oblique incidence. So very first of all we shall be taking the case of normal incidence. So if here we have this line to be acting as a boundary here and on this side we have a perfect conductor. So for perfect conductor there won't be any possibility of having microwave inside this particular medium. So whatever the microwave incidence here will be reflected back. So this is actually the case of oblique incidence. Or else if you consider this to be the line as a boundary here into the medium one, we shall be writing here the incident wave. So here we can write E suffix I, H suffix I, the incident electric wave, incident magnetic wave. So this will be the portion that is reflected back. So this is E suffix R, H suffix R here, and some of the portion will be transmitted into the medium 2. So that can be given as E suffix T, H suffix T here. So these are the incident electric and magnetic waves, these are the reflected electric and magnetic waves, and these are the transmitted electric and magnetic waves. So the case we are talking about the normal incidence. Now for the medium one, as we have EI, HI, ER, HR, here actually we find the reflection here. So for medium one we can have the definition of a reflection coefficient. Generally the reflection coefficient is denoted by this capital gamma. Now this is reflection coefficient I write. To have a formulation of reflection coefficient, we take the help of impedance into the medium here. So for medium 1 we can write eta suffix 1. So eta suffix 1 is actually the ratio of the magnitude of electric to that of the magnetic component. So here in terms of the permeability and permittivity, we find it will be under root of mu1 divided by epsilon 1, and we can write eta suffix 0 divided by square root of epsilon r1 here. So generally we have permittivity epsilon is equal to epsilon 0 times epsilon r. So this is for the free space condition or air, and this is the relative permittivity constant. So if you account epsilon 0 into this eta 0 intrinsic impedance for the free space, the value you can put 377 ohms. So that time this will be the formulation for eta 1. Similarly, we can have the formulation of eta 2 for the medium 2. So for medium 2 we shall be writing eta 2. So it will be given by square root of, here we have mu 2 divided by epsilon 2, and in short we can give it as eta suffix 0 divided by square root of epsilon r2. So this is for the medium 2. So as in the medium 2 we find that few of the portion has been transmitted, we define here transmission coefficient. So transmission coefficient is denoted with the help of capital T letter. I mention here, this is the now we have eta 1 the impedance into the medium 1, eta 2 the impedance into the medium 2. So these are actually the ratios of E to that of the H. So with the help of these particular symbols we can have the formulation of the reflection coefficient and transmission coefficient. So for the normal incidence case, the reflection coefficient capital gamma can be given as capital gamma will be equal to eta 2 minus eta 1, eta 2 plus eta 1. Now the transmission coefficient can be given as 1 added with the reflection coefficient capital gamma. Hence we can have it to be equal to twice eta 2 divided by eta 2 added with eta 1. So this way we can have both the formulae for reflection and transmission coefficient. Now if it is the case of reflection, so that time the standing wave ratio is also acting there. So standing wave ratio generally we abbreviate with the help of capital SWR. So it is sometimes also denoted by rho, and it will be given in terms of the reflection coefficient. So in the numerator we have 1 plus reflection coefficient that just now we have formulated in terms of eta 1 and eta 2, and it will be divided by 1 minus reflection coefficient. So these are the three important formulae as far as the reflection of uniform plane microwave is concerned, taking the normal incidence. Now for the reflection we talk about the second case where the oblique incidence is to be considered. So if this is the line that separates medium 1 from medium 2, and we consider from medium 1 this is the incident wave. So few of the portion will be transmitted here and few of the portion will be reflected back. So for incidence we take at the incidence point a normal here to the boundary surface here. So there will be the angle of incidence that we can denote theta suffix I. So for the reflected wave we can denote theta suffix r, the angle of reflection, and for the transmitted wave we can denote the angle of transmission theta suffix t. Now if for this oblique incidence, here it is the incidence wave. In the incidence wave you can resolve the E component and H component into the tangential and normal parts. So generally if the E component is like this, that is parallel to this particular boundary surface, we can say that E is in the plane of incidence. So for such a condition, we can have the formulation, the direct formula I give you, that is the reflection coefficient given by capital gamma. So it will be obtained by eta 2 cosine of theta suffix t minus eta 1 into cosine of theta suffix I divided by, in the denominator here we have eta 2 cosine of theta suffix t added with eta 1 cosine of theta suffix I here. So as we have formulated the reflection coefficient E to be in the plane of incidence, we can also formulate the transmission coefficient. So transmission coefficient is given by capital T. So capital T, it will be is equal to twice eta 2 in multiplication with cosine of the angle theta suffix t divided by eta 2 cosine of theta suffix t added with eta 1 cosine of theta suffix I here. So this is the transmission coefficient. Earlier was the reflection coefficient. For the case considered that E is in the plane of incidence here. The another case we can consider that H component is in the plane of incidence. That means the H vector, magnetic field intensity vector, into the incident wave is parallel to the boundary that separates medium 1 from medium 2. So in that case, we can have the two formulae for reflection coefficient and transmission coefficient. So the reflection coefficient is given by capital gamma. This is equal to eta 2 sec of the angle theta t minus eta 1 sec of the angle theta I. This is divided by, here we have eta 2 sec of angle theta t minus eta 1 sec of angle theta I. So having the reflection coefficient, transmission coefficient is given as 1 plus gamma here. So capital T, we write it is twice eta 2 sec of the angle theta suffix t divided by eta 2 sec of angle theta suffix t plus eta 1 sec of angle theta suffix I. So I outline both of these formulae. So this was the video from the chapter number 1, Introduction to Microwaves. The motive was to have the introduction to the uniform plane microwaves, and if it is having a propagation from medium 1 to medium 2, it has to face the reflection and transmission also. So I hope you have liked this video. For more information, you can subscribe to Ekeeda channel. Thank you.